My name is Vikram Iyer from the University of Washington, and today I'm going to be presenting FingerIO. This is joint work with Rajalakshmi Nandakumar, advised by Shyamnath Gollakota and Desney. So I'd like to start off by, oh, that's not good. Let's go back to the beginning. So I'd like to start off with a question. Is that coming up there? No. There we go. So I'd like to start off by asking a question. Can we achieve finger tracking for near-device interaction with absolutely no instrumentation of the finger and without any need for line of sight to it? If we could do this, we could think of all kinds of exciting applications that we would enable on smartphones and smartwatches. So one example that we actually built, or a few examples that we built, are you could imagine putting your smartphone on a table and then using it to track your finger motion, even when it's not on the screen of the device. And without any additional hardware, you can turn anything into a drawing surface. Imagine this would be even more useful on a device that has a really tiny screen, because now instead of trying to draw something on your smartwatch, you could make gestures on your skin or perform some kind of gesture in midair to control the device. And lastly, if you don't need any line of sight, then you could even perform interactions in the presence of occlusions. So let's say I could put my phone in my pocket and then do some simple gesture to change the volume. So this is a problem that's interested the HCI community for some time, and recently people have been exploring radar solutions to this problem. One of the notable examples of this is Google's Project Soli, which uses the Doppler shifts in very high-frequency signals to identify certain gestures. But from a technical perspective, while this is very interesting, it has two key flaws that prevents it from being adopted on mobile devices. The first is that these radio waves are traveling at the speed of light. And so in order to get centimeter level finger tracking or any kind of centimeter level resolution, you need gigahertz of bandwidth that you need to process on some small mobile device. And this just adds a lot of complexity and isn't really practical. The other problem is that you actually need this radio that's capable of transmitting your high frequency signals. And so that would mean adding yet another radio to your mobile device, which already has Bluetooth, Wi-Fi, whatever else. And that would consume additional power, area, etc. And that's something that all device manufacturers really want to avoid. So with FingerIO, we take a different approach. And we demonstrate actual finger tracking, not just classification of certain gestures, using no instrumentation of the user and without the need for line of sight to the finger. We do this by introducing novel algorithms and techniques to transform an ordinary mobile phone or smartwatch into an active sonar system without the need for custom additional hardware. We demonstrate that this system is capable of achieving an accuracy of 0.8 centimeters when we tested on a Samsung Galaxy S4 and 1.2 centimeters on a smartwatch prototype. When building this system, we faced two key challenges. The first was, how do we even transform an ordinary mobile phone or something into an active sonar system? And the second is, using that system, how can we get sub-centimeter level finger tracking? I'm going to talk first about this first challenge of how we can build a sonar system using a mobile phone. So at a high level, the way that sonar works is by transmitting out pulses of sound waves and then measuring reflections of these sound waves off of various objects in the environment. So in our case, we use the speakers that are built into a phone to transmit these audio signals, and then we measure the reflections of these off of the moving finger on the microphones that are also built into the device. So when the system is running, the speaker is periodically emitting these pulses of sound. And then what we leverage is the fact that as the finger moves, the amount of time that it takes for these pulses to reflect off of the finger and arrive back at the microphone is going to change. And so we also know that even though there are all kinds of things in the environment that are going to be reflecting sound, the finger is actually moving. And so over time, the amount of, or the the arrival time of these echoes is actually going to be changing. And that is what we're measuring. So the question here is, how accurately can we resolve the arrival time of these echoes? Because sound travels much slower than the speed of light, by sampling at 48 kilohertz, which is available on most mobile phones, we can achieve timing resolution of one sample that corresponds to a distance resolution of 0.7 centimeters. Now, because we have two microphones on a mobile phone, we can combine these two measurements to achieve 2D finger tracking with sub-centimeter resolution. So now that I've explained at a high level how Sonar actually works, the question is, can you achieve sub-centimeter accuracy in practice? I'm going to talk a little bit about this now and some of the challenges that we faced here. So the key here is we need to accurately identify when an echo arrives at the microphone. And so a first order solution to this problem would be to transmit a signal like a chirp that has a very high autocorrelation. Then we can correlate the received signal with the transmitted signal and use that to get the time that it arrives. So here's an example of what that might look like when we do this correlation operation. Mathematically, each of these peaks corresponds to an echo arriving at the microphone. As I mentioned before, we can see there are many of these peaks in the signal, and those correspond to all the things that are reflecting sound in the environment. But again, we are interested in measuring a moving finger. And so the key assumption that we make is that the closest moving echo is what corresponds to finger movement. And so now we can look at an example of what might happen as we're actually tracking a finger. Here we can see that this echo is clearly moving closer to the phone, and that's the finger movement that we're actually tracking. So we tried implementing this correlation technique, but with various different signals that we tried, we were only able to achieve an accuracy of 2 to 3 samples with which we could resolve this arrival time. And that translates to an accuracy of about 3 centimeters. And while that might sound really great and is better than what others have achieved with these systems, the problem is that 3 centimeters is still about twice the width of your finger. And so we needed to figure out a way to get the exact arrival time of an echo, to get sub-centimeter level resolution. To solve this problem, we looked to wireless networks for inspiration. Specifically, if we look at Wi-Fi, we can see that you have a transmitter and a receiver that aren't synchronized in any way. They don't share any kind of common clock, but somehow the phone or whatever is receiving Wi-Fi packets has to figure out exactly when a message starts in order to successfully decode it. The way that Wi-Fi solves this problem is using a technique called orthogonal frequency division multiplexing, or OFDM for short. I'm going to explain a little bit about how OFDM actually works and how it achieves good timing accuracy. So for OFDM, you start out with data in the frequency domain. In our case, we don't really care about sending data, but we can just take random values, and we can take an inverse Fourier transform of these frequency values to generate a time domain signal that we could actually transmit from our speaker. Now, the key to leveraging OFDM for achieving timing accuracy is to take the first part of that signal, the first few samples, and simply append it to the end. So intuitively, we now have a signal that over this time period looks somewhat periodic. And if you think back to any kind of basic signal processing you've taken, remember that periodic signals have all kinds of useful properties that we can exploit in the frequency domain. Specifically, we note that timing errors are going to correspond to phase offsets when we take a Fourier transform. Let me walk you through exactly how this works. So if we start out with the case when we know exactly when a signal arrives, we take a Fourier transform starting at exactly the beginning of our OFDM symbol. Then if we look at the phase, it's going to be perfectly flat and constant over the different frequencies. But then if we have just a one sample error, then we're going to see a slope in the phase that continues across the different frequencies, which is a well-defined slope of 2 pi in the case of a one sample error. Now, if we increase this error to 2 samples, then we suddenly have a slope of 4 pi. So there's a linear change in the slope of the phase whenever we have a time offset. And so using this, we can correct any kind of inaccuracy we have in estimating the beginning and get the exact time of arrival. So now, to put this all together, as I mentioned before, we're going to be continuously transmitting these pulses in our sonar system. And in this case, we choose our pulses to be OFDM symbols. We design these to be in the range of 18 to 20 kilohertz, which is above the range of adult human hearing. And we transmit them, we space them apart by 5.92 milliseconds. We chose this number because that's the amount of time that it takes for an echo to go from the phone out to a distance of 1 meter and back. And that's the maximum range that we were interested in looking at. So the second thing that we do is to get a coarse estimate of the timing. We can use correlation, as I mentioned before. And that'll get us to within 2 to 3 samples of the actual arrival time. And then lastly, we can leverage this phase property that I just talked about to get the exact time of arrival and get our sub-centimeter level accuracy. So now I'm going to talk a little bit about the evaluation that we did to see how well this system performs in practice. The first question that we really had was, how accurate is FingerIO? If we look, we did a user study with 10 different users, and we asked each of them to draw a pattern of their choice on the screen of a smartphone. And at the same time that they were drawing this, so we had our reference, we ran FingerIO on a separate smartphone that was placed 25 centimeters away. We compared FingerIO's estimates with our reference drawing on the smartphone touchscreen and saw that we had an agreement of 0.8 centimeters. This is a median value, and the maximum error that we saw across all these experiments was 1.2 centimeters. If anyone's interested in the exact distribution, we have this in the paper. We also did these measurements at different points in a 50 by 100 centimeter grid around the phone, and we found that these results were pretty consistent. I'd like to show you now some of the examples of things that users actually drew. We can see here that in black we have the reference drawing that was taken by the smartphone touchscreen, and then in green we have FingerIO's estimates. I'd like to note here that the X and Y axes are actually in centimeters. And so these are very small drawings where if you didn't have centimeter level accuracy, you wouldn't be able to get anything that's close to reconstructing the drawing. We also wanted to test how our system would perform on a smaller form factor device like a smartwatch. Unfortunately, there aren't any smartwatches on the market that have 2 microphones. So we built our own smartwatch prototype to see how this would perform. In our case, this is just a simple plastic case that had 2 microphones in it, as well as a speaker and some recording electronics. We did the same kind of experiment, where in this case we had users wear our smartwatch prototype, and while we did this, we had them draw a shape on a smartphone touchscreen, so we had a reference. When we compared these measurements, we got an accuracy of 1.2 centimeters over an area of 25 by 50 centimeters. We note that the accuracy of the smartwatch wasn't quite as great as the smartphone. This is most likely just because of our recording electronics and some, we didn't really optimize the system for noise performance or anything like that. We're confident that a future solution could achieve better accuracy similar to a smartphone. So the last question that we had, one of the practical challenges that we have to address in the system is how do we figure out when a user is making the motion that we want to measure, if it's going to be constantly tracking a finger. To address this, we designed a specific gesture that could be used to start and stop this system. So here, the gesture that we chose was a simple swipe to the right and then a movement to the left that occurs very close at a distance of less than 5 centimeters from the phone. We were able to identify this with greater than 90% accuracy. So then our question became, how many false positives do we have when we compared this gesture to just random finger motion? We had our 10 users each draw just random patterns for a period of 1 minute each. And then we analyzed that data in both the case of the smartwatch and the smartphone to see if we ever falsely identified this start and stop gesture. In the case of the watch, we had 0 false positives, and in the case of the phone, we had 2 that actually were both from the same user, which suggests that there isn't any kind of systematic error here. So I'd like to conclude by summarizing FingerIO's contributions. We demonstrate tracking a finger with absolutely no instrumentation of the user and no line of sight to the finger. We do this by introducing novel algorithms and techniques to transform ordinary mobile phones and smartwatches into active sonar systems without the need for additional hardware. We hope that FingerIO enables all kinds of exciting new directions for research in this space, and that others can, or that we as a community really can build on these techniques to achieve even more exciting things, like tracking multiple fingers or complex 3D gestures in the future. Thank you.
Okay, so we have time for questions. Do we have any questions? Yes.
Hi, my name is Evan Strasnick. I'm from Stanford University. Thank you so much. This was awesome. I was curious if you ever evaluated or did any evaluation of the system for user in motion. It seems like your primary assumption that the finger is the closest thing moving might break down at that point.
Right. So at this point, we haven't really tested a finger in motion, but we're pretty confident that using some additional techniques by leveraging other sensors on the phone, like an accelerometer, you may actually even be able to get better performance. Because you could think of then, if you had measurements of exactly where your phone was, you're essentially creating an antenna array type of thing, where you can combine measurements from multiple different points in space to possibly get better accuracy or something like that.
Thank you.
Hi, Gregory Abott. I'm confused here because I don't understand your line of sight point, because if you had the phone sitting here and you had another phone like that and you were moving your finger like this, there's no way this would work.
Right. So what we're talking about for line of sight is really line of sight through anything that sound can pass through. And so that's going to be dependent on the material. In our case, we were really testing for things like fabric. If you had a very loud speaker, for example, you might still be able to get echoes.
Okay, yes. You just need to use a different term than line of sight.
Sure.
Okay.
Hi. Daniel Ashbrook, Rochester Institute of Technology. I'm curious, you restricted the range in which you could operate this, but I'm wondering actually how far away you could be and still successfully use this.
Yeah, so the range choice that we made was specific to our implementation. In principle, you could use these same techniques with, say, a louder speaker or something at a greater distance. We chose the 1 meter distance as a nice trade-off between where we could detect our minimum signal level and, as a way to ignore any kind of movement that's happening beyond that 1 meter range.
Thank you.
Hi, Gerard from CMU. So in your experiments, were the motions of the fingers always moving, or did the user stop at any point? Were there any differences in accuracy when the finger stops? Because from my understanding, the tracking is dependent on motion. Is that correct?
So what we were tracking was continuous patterns. If the user stops, then our system doesn't actually track that because we're looking at moving echoes, like I mentioned. So what we do is we actually threshold our signal to figure out when we actually have a moving echo, right? So when a user stops, we would just keep reporting that same point. The other problem is that because we don't have 3 microphones, if you take your finger off the screen, if that's what you're referring to, we can't resolve this. In a future system with an additional microphone, we might be able to do that as well.
So is there a drop in accuracy when a user stops?
No. So we would just continue reporting that same point because really at that point you have a drawing that just stops at one point, right?
I see. So I guess, have you done any tests where the finger stops and then there's a report of any change in the signal that's being measured while the users, because it's some gestures require you to stop or some gestures require you to move. But from what I understand, there is a requirement of motion.
Right. So again, the way this system would work is that when a user does stop, we just continue reporting the same point. And so if you're interested in a specific gesture that stops for a period of time, then you could look at when this point stays constant over time, and then the user would start moving again, and then we would start tracking different points. Does that answer your question?
Sure. Thank you.
Yes, just want to know, as you use Sonar, so is this FingerIO sensitive to environment noise? If so, do we have figure out this problem?
Right. So we actually did some evaluation of other noise in the environment in the paper. And as I mentioned before, the way the system works is there are going to be changes in the environment, but we're specifically looking at a moving finger. So some change that's happening over time in these echoes that we're measuring. And specifically, we look at the closest changing echo. And that's what we identify as finger movement.
Okay.
Hi, Corey Pittman, Central Florida. How well were you able to isolate the finger's movements from the rest of the hand? So when you were running your user study, did you have to tell people don't move your hand while you're, focus on moving your finger and not moving your entire hand because that would be tracked as well?
Right. So for the applications that we were looking at, where you're actually drawing something, because your finger is really connected to your hand, the dominant motion that we would be measuring would still follow the same pattern. So that didn't really make a difference for us.
Okay, that could still be an issue in some cases if people wanted to just draw a small
so
fine
we can't do
movement.
something like tracking the exact hand pose with the limitations that we have right now, but future work could definitely expand on that.
Okay, thank you.
Okay, thank you very much. So this paper would also now even mention